For problem statement 1, we have a time-dependent one-dimensional heat conduction through the thickness of a rocket metal casing. The inner surface of the casing is exposed to a hot combustion gases around 300 Kelvin. So the importance of this study is to prevent a catastrophic failure, to understand the thermal stress and fatigue of material, and to help selecting the best material. Why is explicit method chosen for one-dimensional time-dependent heat conduction? Because it is easy to calculate and program, sufficient accuracy for some practical engineering applications, stability and convergence depend on spatial and time step sizes governed by the dimensional stability parameter, which require less or equals to 0.5 for accuracy. So here is the derivation of the equation. Okay, so now here is the coding for the explicit method. We have the parameters, casing thickness, density of fall, the ambient temperature, and the specific heat. Also, the thermal conductivity is already being made into constants. So here is the input. So the user need to put the number of spatial intervals, the hot temperature in Kelvin, the time step, and also the total simulation times. So this one is NT that will calculate for the number of time step that is needed. So we have the fine grid for the error estimation. So, here we have the explicit method function. So the function will calculate the dimensionless parameter that is R. If it exceeds 0.5, then it will become unstable. So here we got the explicit method functions formula where TO equals to T, and yeah. So here we calculate the T final is equals to T. So here we have the soft explicit functions for the T cos and the T fine. And then for the coordinate, the grids, the X cos and X fine. And we also interpolate the fine grid to cos grid. So we have the approximation error between the fine and the cos. And the result will be displayed in the tables for the intervals, position, cos, and fine, and approximation error. And then we plot it using the last coding here. That's all. So the user is required to input the spatial intervals, time steps, the temperature of the combustion engine, and also the total simulation time. So the outcome, the user is expected to have the result table and also the graph. So for the program demonstration, we can see that the user input number of spatial intervals of 5, the hot temperature is 5000 kelvins, and the time step is 0.1 seconds, and total simulation he chose is 5 seconds. So he got the graphs as promised, the temperature distribution comparison between the cos grid and the fine grid, and also the table that he got. Yeah, that's basically what is the output of this programming. So next for the input obtained by the user is this one. And then you got the graph and the result table. So based on the result achieved in the previous slide, we can see that the accuracy of the method depends on the time step size. Smaller is better. And the efficiency of using this method are low computational cost per time step because they only involve direct calculation. And it is convergent provided that the dimensional stability parameter is below than 0.5. The effect of step size causes various outcomes. It may be unstable if it is too large. And the programming difficulty is very easy to implement. The advantage is the explicit method is very simple to understand and implement. The update formula directly calculates new values from previous ones. The economical cost per step as each step involves only direct calculations. No need for metric system to solve unlike implicit methods that could be hard to program. So, lastly for the limitations, the conditional stability and convergence depends on the dimensional stability parameter which are needed to be lower or equals to 0.5. If not, the result produced might oscillate and diverge from the real solution. This method also will struggle with stiff problems and require a lot of small time steps to solve them.